Okay, can you see my chart?
Yes, we can.
Okay, fantastic. Let me start my phone here. Okay, so thank you all very much, Samir and Mike in particular, for having me here today. It's an honor to be here. It's quite a list of speakers, and I look forward to watching many of the talks today, and I've enjoyed the first couple so far. So Samir asked me to give a brief overview of HPC and CFD at NASA. I've known Samir for many, many years, and so I'm happy to do that. He has helped me on innumerable occasions, and so thank you for having me, and I will try and give you kind of a 50,000-foot overview very quickly over the next few minutes. For those who aren't familiar with NASA, I'm kind of showing some of the facilities around the country. We're primarily research centers, flight centers, and locations where we, build flight hardware, basically. And so I'm at NASA Langley in Virginia right now, on the right side of this. This picture. And so now I'm going to kind of annotate this picture a little bit to give you a little bit more feel in terms of the CFD that's being done at the agency. First, I've popped up a blue set of text here. This is where our large HPC facility is out at NASA Ames in the Bay Area. Many of the centers have mid-range facilities, but this is really where the big iron sits for the agency out at Ames in the Bay Area. I'm adding some green stars now to give you a feel for where CFD is applied at the different centers. So Glenn, Ames, JPL, Armstrong, Johnson, Langley, Marshall, and Kennedy. You will find some form of Aerosciences CFD going on there. There's certainly other CFD across the agency. So for example, for weather simulations at Goddard, for example, but for the most part, for Aerosciences CFD, aerodynamics and space aerodynamics and so forth. These are the primary centers that are involved, and then I will add one more red star here to indicate where most of the development activity is. And most of this happens at 3 research centers, namely Ames, Glenn in Cleveland, and Langley out here in Virginia. So that's just to kind of give you a feel for where the development, the bulk of the development is happening at least. And then finally, I'll add some of the major codes that come out of those centers. By no means is this an exhaustive list across the whole agency, but these are most of the big ones that are doing most of the production level and high-end research type simulations supporting engineering and research. So a couple up at Glenn, a few out at Ames and at Langley, and these really run the gamut from lower order, second order type codes all the way up through very high order methods, Cartesian codes, unstructured codes, body fitted structured, Euler and Navier-Stokes up through LES and a little bit of DNS as well. So just to give you a lay of the land there. About 6 or 7 years ago, NASA commissioned a study called that eventually became known as the CFD Vision 2030 study, and it was basically led by Boeing and a number of other industry consortium members and universities. And NASA put the activity together to try and lay the groundwork for what is needed across the aerospace CFD community for what will be needed to achieve what we need to accomplish roughly in the year 2030. And so Boeing led a fantastic study. It's an easy read. I encourage you to look this up if you get a chance. It's very informative. And essentially, if you're doing CFD at NASA, you better be able to show alignment with this document. So this has been used for advocacy all the way up to NASA headquarters and beyond, up into OMB and so forth. So it's a pretty interesting read. And to basically summarize some of the goals, I don't think this is any news to anybody here, but for one thing, we have to do more high-end physics-based, higher fidelity predictive modeling. So, we're starting to move beyond RANs and URANs, and we find the need for many of our applications and configurations, advanced configurations, they call for accurately predicting mildly to massively separated flows. And so we have to start getting into large eddy simulations, or at least some kind of hybrid simulations. Chemically reacting obviously is important for things like reentry, radiation, all the other multi-physics and multidisciplines you might imagine with a modern aerospace vehicle. Dealing with errors, uncertainties, this has obviously been a big thing across the community for the last couple of decades, and we've got to get a handle on this and dealing with our margins and so forth in designing spacecraft. How much weight do we need for a heat shield on the next mission versus, what's safe versus what can we get away with, for example. Automation is a huge thing. I think this doesn't come as a surprise to anyone either. Getting the human out of the loop to the greatest extent that we can. That's a tall order, but I think there's slowly been making some headway there. And obviously on this crowd, it's not lost that the HPC challenges are immense. The architectures that are coming fast and furious now. How do we deal with all the multiple or the memory hierarchies, the very diverse heterogeneous processors that are coming our way, and how do we keep our software agile in this type of environment and able to move forward in a timely manner. Flexible use of these HPC systems. So there's a great tug of war I'll talk a little bit more about in terms of capacity versus capability. Both of them have their place, but it can be tough on limited resources to achieve both the needs of both. And finally, it goes without saying that multidisciplinary and multi-physics type stuff, not only from the analysis perspective, but ultimately in the design context as well, are super important going forward. So I'd encourage you to check out that study if you've never come across it before. I can hear some case that cross our deck, and this really kind of would be an asset thing most every day. And so most of our NAT applications, but being tagged, most of these codes end up on the with the company, and we get some pretty interesting problems thrown at us, not only but think automotive. So typically we do have Aerosciences with the French, Boeing, Northrop Grumman, Lockheed, Gulfstream, those types of groups. And you say this is a hope on bad moon in the next year, and our next 10 to 20 years. We supersonic, that's very hot these low boom commercial craft. Crafty retypos coming back in tariff, back first at 20,000 per speeds, very innovation. That's the first order and crafted in the Aerosciences. That's a high on problem. Propulsion, so whether it's turbofans, turbojets, ramjets, basically a lot of areas when things like DoD we partner on with DoD evaluation. The thing this is landed on the computers to do land winds. There was the solar on this actually under
excuse me, Eric.
Those
excuse me, Eric.
yes.
Hey, your audio seems to be very garbled. So do you mind using the phone for audio?
Or perhaps when the video goes away, it'll be better.
Okay.
Okay. I'm sorry. Is this better now?
Oh, this is much better.
It is. Yeah, yeah.
Oh, okay. I'm sorry. I'm not a WebEx guy. I'm usually on something else, but
No. Sorry.
okay. I apologize for that. Yeah. So let me dig into a little bit of capacity versus capability, and this is fundamental when a fundamental challenge in a resource-constrained environment. So on the left, if you're familiar with, say, the Euler equations, very simple PDEs that ignore the effects of viscosity, and then as we march towards the right on this plot. Increasing physics, but obviously at an increased cost. So you get up into RANs. This is largely where most people are getting their work done in a production type environment these days. So here we're modeling the turbulence. It's often smeared out, but you're getting some gross effects of it. And then again, what we're finding is the advanced concepts, we really need to be getting into things like LES, where you're resolving at least some of the larger scales with the numerics and maybe a hybrid approach with RANs, for example. And then way downstream, obviously talking about things like DNS, but that's a ways off. So again, a lot of the people I think you'll find in practice in the engineering spaces at least are using Euler or Navier-Stokes certainly now, hundreds to tens of thousands of CPU hours on very moderate resources. But the vision calls for prediction of unsteady separated flows, and so that's really where the challenge lies. there's been some predictions or projections made for full aircraft wall-modeled LES. Is you're looking at a grand challenge problem sometime in the 2060 timeframe there, with an entire leadership class machine of that era to actually do a problem like that. And so this is kind of the tug of war we're up against. But for now, I would say hybrid RANS LES and some canonical wall-modeled LES is being done, particularly at lower Reynolds numbers. But these are simulations. They're kind of out there on the bleeding edge in terms of hundreds of millions of CPU hours on a large HPC resource. And then here on the right, I've got a table that I got from a colleague at Ames. This is a fantastic example of capacity computing. You know, you can imagine for before we fly any new vehicle, or industry does for that matter, you typically are generating very, very dense aero databases to characterize how that vehicle is going to fly and how it's going to respond to controls and so forth. And so, you know, in the space of a month or two, you know, there's folks that are generating tens of thousands of Navier-Stokes solutions on the machines, on the systems to support, in this case, the Space Launch System development. And so every 2 months, the design may change, go through a design iteration, and you're back to generating several, you know, tens of thousands more simulations. So that's an example of capacity computing, but it really shows this disparate nature with trying to also get in the capability work. And so I've got a little cartoon here from my experience over the last 20 years here. It's a cartoon, number of cores across the x-axis in a log scale here, and I'm kind of waving my hands. But if you go back about 20 years, one of the hats I wear is here in the Fun3D group at Langley. We worked with the PETSI team in the mid-90s, right when PETSI was kind of in its infancy, and that collaboration was very successful and won a Bell Prize at the time for implicit CFD for aerodynamics on about 2,000 cores on some of the large Sandia machines at the time. If we come 15, 20 years in the future, the Chinese a few years ago essentially won a Bell Prize for implicit CFD for weather prediction on 10 million cores. And so in the space of 15 to 20 years, you're talking about growth of, say, 4 orders of magnitude in complexity. But here's the issue. When we look at what the agency is typically doing to this day, the simulations are generally, you know, 500 to a few thousand core type jobs still. And so that's again an illustration of, you know, this tug of war between being able to do the really high-end, you know, stuff, the discovery type work that HPC is really geared for, or, you know, the equally valid or important capacity type jobs supporting, you know, real mission development and so forth. Some other challenges I thought I'd touch on. I think it goes without saying, reliance on computing is rapidly expanding with loss of facilities, you know, budget constraints and so forth, increase in application complexity, again, with multi-physics and so forth, and just the lack of ability to test. So if I want to land on Mars, I can't test that on Earth by definition. And so we have to become almost wholly reliant on computing to be able to understand those physical phenomena. Amdahl at the macro level. So we all know what Amdahl's law is, but I often like to think of it in terms of the entire engineering workflow. So we pull our hair out getting our fluids code or our structures code to scale well, but you know, if you look at an engineering workflow for generating, you know, aero databases or large capacity type simulations that the engineer's doing, there's a lot of little pieces there that we don't take into account all the time, and Amdahl will bite you, you know, just as it does at the discipline level if you don't have all the little pieces, you know, able to scale in those environments. So that's a big challenge for us. The ever-expanding gap between state of the practice and state of the art. So again, I harken back to that slide on the previous slide. You know, you've got users that are predominantly running 1,000-core jobs, whereas, you know, if you want to get onto one of the leadership class systems, for example, at DOE, you're looking at your proposal better show, you know, that you're able to at least go to the neighborhood of 1 million cores or equivalent. And so you're asking folks, you know, who to move up 3 or 4 orders of magnitude, and that's a very, very tough gap to bridge, and that's only going to get more harder, presumably, as the 20% kind of mandate, leadership class mandate, moves on to Frontier or the other leadership exascale systems that are coming. So that's a tall order for us. Long-term agency level software strategy. So an ECP at DOE or a CREATE at DOD, these would be unheard of at NASA. And so we struggle to fund long-term sustained software development where software is kind of a first-class citizen, a first-class deliverable. So the next bullet, it's very difficult to reposition our tools for new architectures in a project-driven environment, essentially. And then this came up in the question and answer session just a few minutes ago. I think we all struggle with workforce recruitment and retention. I'll give you a little bit of feel for code development. Our typical development teams range from a couple of people to maybe order 10 people. Some are full-time developers, others are full-time applications people, or most are somewhere in the middle. Most are co-located, although some of the larger codes are more geographically dispersed these days, and certainly with COVID, we're learning a lot of new ways to work. Codes can live decades in this environment. So if you look at a code like Overflow, that was born out of the early 80s, the shuttle program, and that is still going strong today, 40 years later. So these are things we have to wrestle with. Clean slates are very rare, hard to come by in a project-driven environment. New features and additions are typically driven by the project needs rather than the core competencies. Some codes do become mainstays across the aerospace industry. So if you go out there to the major aero companies, at least in the US, you'll probably find a lot of NASA codes at the heart of their workflows. Very broad range of approaches spanning Fortran, C, C++, and everywhere in between. Most efforts do develop homegrown implementations for various reasons. I think there's a lot of pros and cons there, but I will say that I think we all do we try to do a diligent job of keeping tabs on what's available out there, though. And so I'm eager to sit and listen through the rest of the day's talks on that front in particular. But for the most part, most groups are a little hesitant to put a lot of third-party dependencies in their stack. But that's not a broad brush statement in general. There are some who adopt some external dependencies. Most teams utilize and are aware of modern development practices to at least to some extent. I know our group has heavily leveraged things like Agile and extreme programming practices for the last 20 years or so. So things like Scrum and continuous integration, test first development, unit tests, and so forth. So I think you'll find a lot of that across the agency as well. I do want to highlight a couple of encouraging recent workforce development activities we've been able to kind of lobby for. One of the hats I wore over the last few years, we got some direct funding out of our director's office here at NASA Langley to support what was known as an HPC incubator. And this was a 3-year activity where we were able to provide some shelter for especially some of our younger folks, some of our new hires and early career folks, to basically allow them to spend time immersing in the HPC community and getting out to some of the meetings, some of the conferences that they don't get to normally go out to under the project structure. And so we had training courses coming in every week or two at our peak, a lot of guest speakers and collaborators coming in. And then the idea during the 3rd year was we really focused on infusing those skills and ideas and concepts back into the conventional projects to try and impact and bring HPC and computational science as a core competency back into the conventional project structures. And I think we had a lot of success there, and we continue to make progress there. The follow-on project, although not designed that way, the hat I'm wearing right now is kind of an incubator at the agency level. So right now we've got an activity spanning about 4 NASA field centers, and we're funded out of headquarters, the Office of Chief Engineer, to basically explore the use of new architectures for our major workhorse Aerosciences codes. And so we've largely focused here on the NVIDIA V100, just because that's kind of the state of the art right now, and we have access to it. So maybe people can go on mute. But nonetheless, this has been a great activity so far. It's allowed us to bring in some test bearer hardware, which is normally not accounted for in our rather meager HPC budget at the agency, and allows us to do a lot of workforce development with training and boot camps and hackathons and so forth. So that's been a very refreshing activity, I would say. I do want to take a couple of minutes to kind of wrap up and give you a couple of examples of use cases. In this first one is kind of the penetration of new architectures into workflows. So there's a lot of efforts, looking at new architectures, I don't want to say in an academic setting or maybe in a research setting, but we're trying to really push these into, everyday use. In our effort and Fund3D at Langley, we've been working on GPUs for close to 10 years, very closely with NVIDIA, and And our code basically shows a 4 to 5x speed advantage between V100 and, for example, a Skylake or a Cascade Lake. And we're memory bound like many other large scale codes. And so that typically correlates with the ratio of the hardware memory bandwidths. And so it seems to make some sense. And then A100 boosts that up to 7 or 8x. So this is a pretty substantial boost for us. And although these nodes are more expensive, obviously, we still do find that they're a win on performance per dollar. And so what I've got here are 3 typical application spaces where we've been able to move into these spaces a little bit with GPUs. Supersonics, rotorcraft, and space launch. So what I've got here is a pair of plots under each figure. The one on the left is kind of a node-to-node comparison. So how do 3 GPU nodes stack up against 3 CPU nodes, for example? And obviously this isn't a very fair fight. So a GPU node is typically a number of GPUs on there. And so it's really not fair to put those head to head, but you know, nominally you see about a 25x speed up there, Xeon versus, in this case, 6 V100s. What is maybe a little bit more applicable is the right-hand plots in each pair here. And so I'll focus on the Space Launch System over here on the right. In this case, we're comparing, you know, we're trying to determine how many CPUs does it take to keep up or keep pace with a certain number of GPUs. And so over here, we've run this SLS simulation. It's pretty complicated on about 66 V100s in about 17 minutes. Whereas it takes us about 14,000 Skylake cores to keep pace. And so you can kind of get a feel for the benefits there, you know, if nothing else, in terms of data center space constraints and so forth, power and things like that. And you'll notice this is a little bit more than 4 to 5x. And generally what we see here is you've got to really strong scale out those CPUs to keep up with those GPUs. And so you're really not using those CPUs as efficiently because you're starting to see your strong scaling tail off there at the high end. And so effectively, it's actually a little bit more than what you see at the device level. So that's kind of what we see right now, at least with NVIDIA GPUs in our current workflows. I hope these videos killing. Maybe I can pause them if I do it. Let me see if I can pause some of these guys here. At scale now, we've taken this GPU capability on Summit. We did a campaign last year on Summit, basically looking at human scale Mars landers. So it's going to take a lander of about the size of a 2-story house to take humans to Mars, about 30 metric tons to the surface. That's a huge, huge jump up from where we're at right now with our little rovers. But basically, we were able to look at throttle settings, flight Mach number, and spatial resolution here through this campaign. Simulations really of unprecedented fidelity we could never dream of doing on our own in-house resources. Very big data involved, so pretty much a steady stream every day last year, moving 40 terabytes a day from Oak Ridge to our archiving facility out at NASA Ames. So some pretty big data and network migration requirements there. You can actually go get some of these data sets on a portal there, but really the name of the game here was the kind of game-changing computational performance. So if you look at a capacity-driven system, you know, with x86s, for example, a problem like this, one simulation, you know, when you sit in queues and stuff like that, you're waiting, you know, maybe 10 days, you know, to run a 5-day job and get back in line again and do it all over again. You're looking at roughly 9 months to do a simulation like this in a capacity-oriented x86 system. Whereas on Summit, we found we were able to stack up as many as 6 runs in an ensemble and put them on about 3,000 V100s and be done in a work week. And so this was a substantial speed up, you know, from years to days for our learning cycle and our engineering workflows here at the high end. And so that's really what we see, you know, a big benefit from not only the architecture, but just the capability class policy on the system. A couple of minutes for questions, but thank you again for having me. I'm really honored to be here, and I look forward to the rest of the day. Thank you, Mike and Samir.
Yes, thank you very much, Eric. There are some questions here in the chat window.
Let me stop sharing so I can get back to the chat, maybe. Chat, okay.
Michael Roos
These
was my
plots
question.
are awesome.
Yeah, we could read them for you. That helps.
Thank you, Mike. I can see them now. I'll try and go, let's see, recruiting. Do you find most compelling in attracting new staff? You know, over the years, the older folks at NASA, they try to lean on well, this is NASA. We do the cool stuff. And that's maybe still true to some extent, but I think we're losing that kind of, it's not the glory days. We're not the Apollo program anymore. And so that we can't lean on that as much as we used to, but we still, I think, are successful in selling the science and the interesting, cool stuff to some degree. And it's just about finding that magic combination of the really sharp guys who just want to do cool things in the aerospace field. So yeah, that's a great question. We hear that a lot. Impediments to adopting third party, I'm gonna maybe leave that for offline. There's a lot of pros and cons there we find, both technical and non-technical. Plots are awesome. Thank you, Christian. We're looking hard at COCOS right now, and I'll return the favor. It's a very awesome piece of software you guys are putting together. I'd love to talk with you some more offline as well. Agree with Ben. Tried to make two also. Did I miss any questions up at the top here? Oh, I apologize for those movies, Samir. I should have known.
Oh, that's great. Thank you very much for a great presentation. And we'll take a short break now, and we'll resume at 9 a.m. Pacific time. There's just one more question from John. Maybe you can address this.
Sure. Oh, John. Good buddy. Over the last 10 years, you've looked at just about every possible way to program a GPU. What's your bet for the future? Great question. We get that a lot. We're all CUDA right now, as you know, and we evolved to that point after looking at a lot of models. And to be fair, the ecosystem really wasn't ready, I don't think, for large-scale applications. Kind of when we were starting, I would want to revisit a lot of, and we have revisited a lot of those earlier programming models. But we've done a lot of work in the last year or two looking at some of the abstractions. So I mentioned we're looking at COCOS right now. That's looking really nice. So Christian, hats off to you there. We've looked at SYCL. We've looked at some of the directive-based models. We haven't, I would say, nailed it down just yet, but I would say that the time is drawing near when we're going to have to make that call and actually inform the rest of the team which way we think is the way to go. And so I don't have a solid answer for you yet, but we need to have one soon, I would say. We can't keep on living like we've been living the last few years. But thank you, John, for that question.
Thank you very much, Eric.